Welcome back, guys, once more. Now we go for a kind of let's call like a simple way of building up dual forms from primal forms, and that's only for linear optimization problems. That's a nice way of starting with the construction of dual problems from their primal forms. Just consider something like this. I have a primal problem defined, of course, for my linear optimization problem, and I want to find its dual. This basically means that my primal is in a given space of variables and my dual is in another space of variables. However, if I solve one, I have the solution for the other and vice versa. But maybe, and just maybe, one of those problems is easier to solve. That's why we tend to find the dual for some problem. Therefore, the dual might help us to simplify the problem and find a simple solution. Okay? Consider this as our primal problem. What could I do to have its dual? It's not that difficult. First of all, if my primal problem is in maximization form, my dual will be the opposite, will be a minimization. Okay? So my dual will be a minimization. And vice versa, of course. If my primal is minimize, my dual will be maximize. Next point. Every bound I have for my constraint will be a coefficient associated to my objective function. That's so nice. Just take a look at this. If I have 2 and 10, those will be coefficients of my objective function, 2 and 10. Of course, I will have a given variable for 2 and a given variable for 10. I will start defining lambda 1 and lambda 2. I must just sum up those two coefficients multiplied by their corresponding variable. Now you can see that if my primal is defined in terms of 3 variables, this particular problem will have 2 variables in its dual form. This basically means, just to start with, here I need to plot 3 axes, and here I can plot just 2 axes. Of course, this will be easier to plot, to graph, and understand how it works, just because it needs less variables. Okay? Next step. I just need to build up the constraints for my dual problem. It's so interesting. I just take this constraint and this, and I suppose this is a matrix. Okay? If I transpose my matrix, I have the values. Wow, is that right? Yeah, it is. 3, 4, and 1 times z. 3, 4, and 1. 1, 2, 3. 1, 2, 3. Those will be the coefficients. This first constraint, those coefficients will be associated with lambda 1, and those coefficients will be associated with lambda 2. Take a look. Exactly. Those are like almost my constraints, okay? What about my bounds over here? My upper or lower bounds, or some sort of bounds we have for our constraints, they will come from the coefficients of my objective function in the primal problem. 3, 6, and 2. Take a look. 3, 6, and 2. I just need to sum up those elements over here. I don't know at this point which are the operators I need to use here. That's not difficult to find. Let's see something. I'm going to give you like a pattern table, but it will make like everything easier to define. First of all, the operators I have in my constraints here, remember, this is related to lambda 1, this is related to lambda 2. This operator will define the space of possibilities for lambda 1, and this the space of possibilities for lambda 2. Take a look. I have smaller than or equal and equal. Smaller than or equal will define the space of variables for lambda 1 and equal for lambda 2. Take a look at this table over here. If my problem is a maximization problem and has this as an operator, smaller than or equal as an operator for my constraint, this will be the way my space of related to that particular variable will happen and must satisfy, basically. If it's equal, it could be like any value. If it's a minimization problem and I have this operator, I can assume just non-negative values for the variable. If it's equal, I can assume any value. Yeah, let's understand this. Is this smaller than or equal? It is. Take a look at the table. Oh, before. It's a maximization smaller than or equal. Take a look. Maximization smaller than or equal. My lambda 1 will assume non-negative values. Take a look. I go back. I don't have like any definition for lambda 1 here, but at this point, after seeing that, I will define that lambda 1 must be greater than or equal to 0. Next, this equal will define the space of possibilities for lambda 2. Okay? If I go to the table, I see maximization and equal. Maximization and equal, it can assume any value. Okay, it can assume any value, so I don't need to define lambda 2 here, because it can assume like any value, it doesn't matter. Okay? What can I do about the operators over here? How could I define the operators over here? Remember, this y has a given space of acceptable values for it. If this first constraint is related to x, this second is related to y, and this third is related to z, and I know that x and z have like no bounds, so what about those constraints related to x and z? Take a look. This is a maximization problem, and here I have y greater than or equal to 0. Take a look now what we're going to do about the table. If in the maximization I can assume any value for my x and any value for my z, those constraints will be equal to their bounds. Take a look like this. Y has to be greater than or equal to 0. What happens if y has to be greater than or equal to 0? Going to the table. Take a look at the table now. What's going to happen with this operator? Variable must assume non-negative values. What about the operator in that particular constraint? Greater than or equal will be here. Take a look. Okay? If you guys have like any sort of issue, there is nothing in the table about the maximization that using this operator as greater than or equal instead of smaller than or equal, what can I do? I can just multiply this constraint by -1 and make it to satisfy my smaller than or equal operator. Okay? What is interesting now is this. I can look at the primal and my dual form, one here, the other here. Just start thinking about the problems. Those both are linear optimization problems. Objective functions are linear. Constraints are linear. Take a look Bounds for the constraint become coefficients for the objective function. Here, bounds for the constraints are coefficients for the objective function. This matrix A was transposed over here. Take a look. 3, 4, 1, and 1, 2, 3. Transposed. The space of possible values that a given variable assumed here will define how its constraint will operate. Z and X have no bounds over here, so they are equal. Here, lambda is greater than or equal to 0, so its corresponding constraint will be smaller than or equal. But lambda 2 has no limit, so no bound, actually. We could assume like any value. So what's going to happen with its corresponding constraint? It will use the equal operator. Here we have a maximization and a minimization. What I want from you now, and I want you to bring to the office hours, remember, every Friday from 10 a.m. to 12, bring your questions. Try to plot this problem, its constraints and everything. This will be very hard to plot actually, but this will be easy to plot because I just have two variables, lambda 1 and lambda 2. That's quite similar to my previous video in which I was plotting with you guys two of the constraints in terms of two variables, and I have three constraints. You guys can plot all those three constraints and try to solve this problem. And then after finding lambdas and everything, try to plot this one and solve it. This one will be more difficult, of course, because it's got three variables, but you guys can try at least, okay? Now, the whole idea that I want you guys to see at this point is that this transformation brings equivalent problems. So my maximization is equivalent to this minimization problem and vice versa. So if I cannot solve one, I can solve the other and vice versa. So of course, depending on the problem I have in my hands, it becomes easier to find the dual for it and then solve it. And not just like start solving it and graphing it and trying to plot the constraints and whatever. Okay. Now I want you guys to try to solve this particular problem. This one. Take a look. This problem, again, it's the same as this. Okay, it's just consider that instead of giving this as my primal, now I give this as the primal problem. I give the other, I give the second as my primal problem. Can I use this primal to find the dual? It's dual? Yes, of course. Is it like the dual is going to be this one? Yes, of course. If I have this as primal, I will have this as dual. If I have this as primal, I have this as dual. Okay? So I want you guys to try that. Try to apply the table at this point. We're going to discuss more on optimization, concepts, and tools, and probably you guys will get like a better idea about what's happening here. I'm sure you're gonna get it. Okay? Now I want you guys to try to solve this problem, this other problem. It's got two variables, two input variables, x and y. It's a maximization. Okay? Try to solve it and watch the video later. Please, don't try to cheat and just take a look at the solution beforehand. Try to solve it before anything. all this time I'm considering for you here, it's a necessary time in the, if we were like inside the classroom, of course. It's really important you guys solve those problems by hand. Okay, could be graphing. Okay, or if you know any kind of algorithm to solve it, try it as well. Okay, see you guys in the next video. Thank you.